saying is constant temperature. And expansion of gases tells us we have final volume larger than initial volume. And expansion is V final larger than V initial. All right. Now the question comes, what is the heat flow for an isothermal process? Because the common understanding is if we do not have temperature change in my initial and final state, the heat flow is zero. But that is not true. That is just not true, all right? And we'll see how exactly or why it is not true by setting up the process and defining a different kind of path for this isothermal process. Remember, when we say isothermal process, we're saying delta T equals to 0, or my initial temperature and my final temperature of the two thermodynamic states, initial and final, they remain the same. But an isothermal process doesn't necessarily require, like, say, your heat transfer is 0. And let's see how that's the case. Let's imagine this is the isothermal expansion we're talking about. We have some kind of system in there. You can imagine that to be some kind of gas expanding, like expansion, right? So the gas itself is having a volume increase in that process while the temperature is kept constant. So in this case, let's say we define our initial state as, say, V initial, P initial, and some temperature T. And let's define our final state as V final, P final, and the same temperature T. All right, so if we look at the process between initial and final state, we have what we want, which is temperature remain the same and my V final larger than V initial. Now, in order to calculate work and heat, we want to define the path. So in this case, the way we define the path is let's insert a hypothetical state. And what we say in this hypothetical state is a adiabatic expansion of the gas. So what that means is we have your V initial goes to V final. My temperature change and my pressure change with it to some kind of initial state, hypothetical state. And it's an adiabatic expansion. All right, so in this process, what we're saying is, hey, let's install hypothetical adiabatic wall around my system. And by adjusting pressure and temperature, we can get the adiabatic expansion of my initial state to a hypothetical state. Right, and the second part involves, well, now my final volume is the same as the final volume we want. We're talking about an isochoric heat transfer between my hypothetical state to my final state. All right, so that's a path we set up for a general situation. It doesn't require ideal gas. We're just saying for a isothermal expansion of my system, we can build this hypothetical path. And now let's use ideal gas as a tool to study how does the work and heat change, or what is the heat and work for each of the hypothetical states, and what is the delta U for each of the hypothetical states. All right. So I'm going to do that on the board so I can keep my process here. But you'll find our work through on the annotated notes. So in this one, let's say we're assuming ideal gas. And I hope people in the back can see me. Okay. And let's write out what we know about ideal gas so far, right? So this is, we covered several times. For ideal gases, we have PV equals to an RT. We have internal energy is only a function of T, and same like enthalpy is only a function of T. And also my CV and CP are constant. Yeah, whatever we build here, they don't have to be ideal. But for us, to simplify our math, let's use ideal gas just to work out what exactly are these numbers, right? So now what we have, in the first process, we say that is a adiabatic expansion of the gas. So for the process, we have Q equals to 0 because it's adiabatic. And for this process, I forgot to say we want it to be a reversible adiabatic. And since it's a reversible adiabatic expansion, we can use W reversible equals to negative PdV. And since we're using our ideal gas law, well, let's see, integral. We're integral between V initial to V final. My pressure is nRT over V dV. All right. And then this integral is something we can solve. Now nRT, well, I'm not sure, we're not sure what's this. So in this process, we can solve this integral by taking nR and T out from the integral. So in this case, again, we can take temperature out because temperature is not really dependent on volume in this case. So what we end up having is nRT and V initial, V final, 1 over V dV, and that gives us negative nRT log V final over V initial. Yes.
How come there's a T prime there? Like,
yeah, so this one is, let me see. I think I made a mistake. We want the temperature, let me see. This one, let me double check to make sure I have it correct. So send me an email later on, so I'll double check on that. But in this process, what we solve is your overall work that's generated. So we have V final over V initial to be a positive number. So my work is a negative. So my system is doing work on the surrounding, and we check this should be a negative value. And then we can use our delta U equals to Q plus work, and that is also a negative number, which is negative nRT log V final over V initial. So this is a negative. And then when we're looking at the second step, we're talking about the volume being kept the same. So it's an isochoric process. So my work in the second step equals to 0. Right. So for the overall process, we have delta U must equals to 0, because for ideal gases, if it is an isothermal process, your initial and final temperature are the same, our internal energy must be kept the same. So for 1 plus 2, so overall, T delta T is 0, so my delta U equals to 0. And for my second part, W is 0, so whatever the heat transfer takes place in the second hypothetical state to final state must equal to the work, the negative of the work that's being done in the first part. So what we end up getting is Q equals to, well, this overall delta U minus the work reversible we calculated, which is nRT times ln V final over the initial. Right. So one of the misunderstanding what we had before is always link heat directly to temperature change. And that's true if we're only talking about specific heat and if we're only talking about a process that's for example, we're dropping the metal into that water, that's the specific heat we were referring to. But when we're talking about thermodynamics, especially when we're talking about two different states, even if we know what is the delta U and delta T for your initial and final state, if we do not know what is the path linking that initial and final state, we don't know how to calculate for Q. And in this case, that's an example of how do we set up hypothetical pathways so we can calculate what is the heat transfer of the process. And it's not necessarily 0 for isothermal processes. Heat is only 0 for adiabatic processes. Any questions here? Yes?
Why did we have to use the work that was reversible in this case?
So that we can calculate what exactly is that number. Now, in this case, if we only want like a qualitative understanding, we can simply thinking about the process, right? So in this case, if it is not reversible, the process of initial state to hypothetical state, it is an expansion. My system is doing work on the system, so my work must be a negative number. And as a result, the heat transfer in the second step must be a positive number. So if we are only looking for qualitative expression, like whether it's positive or negative, yes, we don't have to specify it to be reversible. But in this case, since we want an actual expression for ideal gases, and that's why I specified reversible. Yes?
So the definition of Q that you gave us before, like CP dt, that's only for
The Q reversible? Sorry, what's the question?
The definition of Q you gave us before, like Q equals CP dt, does that only apply to like no changes of state?
Well, so the way we put it is for ideal gases. This is the only time we say that the du equals to Cv dt or dH equals to Cp dt. But remember the actual definition for these heat capacities, if we do not specify ideal gases, then Cv is defined as a partial derivative of U over T at constant V, and Cp is defined as partial derivative of H over T at constant P. So these are partial derivatives. They only become normal derivative when we talk about ideal gases. Yes?
Why is it that delta U is non-zero over there, but then it is over there?
So if we're thinking about the first part, right, so in the hypothetical state, my system is doing work on the surrounding while the heat transfer is 0. So because of the first law of thermodynamics, my delta U must be conserved. So delta U must equals to Q plus W. And since Q is 0, W is not 0, this first process, delta U must be non-zero. And hence the second time we have that to balance up like what we did, because we want the overall process to be delta U equals to 0. So again, this whole question here is trying to demonstrate that whenever you see isothermal, it doesn't necessarily mean heat equals to 0. That's all. That's a whole take-home message. If you're gonna remember anything, like whenever you see isothermal, don't write down Q equals to 0 too fast. Think about it. All right. Next up, now let's think about a different situation, which is the adiabatic process of a perfect gas. So again, yes.
Sorry, for the previous, this example on the work, if it's isothermal, can we say delta U equals 0?
Delta U equals to 0 if we're considering the initial state to the final state. But the initial to the hypothetical state, delta U is a negative number. The hypothetical to the final state, delta U is a positive number. They add up to 0. All right, so, but between your initial to final state, yes, my delta U must equals to 0 because my delta T is 0, and we are talking about an ideal gas.
Okay, so if it's ideal gas and then isothermal, delta U equals 0.
Correct. Yes.
But like, not one or the other. Like if it's an ideal gas, but it wasn't, if delta T wasn't 0, that delta U would not be necessarily 0.
Right, because for ideal gases, my internal energy and enthalpy is only dependent on temperature. Right, so that's one of the property of the ideal gas. Or the other way to put it, for an ideal gas, if my internal energy change is 0, my temperature change must be 0. All right, so if we go one more step back to the Joule-Thomson experiment, for example, we're talking about a isentropic process where delta H is kept 0 for the Joule-Thomson experiment. Now, for dealing with an ideal gas, the Joule-Thomson experiment, let me go back one time. We have mu Jt is measuring the change of temperature with respect to pressure at constant enthalpy, or my Joule constant, mu J, is the partial derivative of T over V at constant U. Now, for ideal gases, if we're keeping H and U as constant, what are the Joule experiment and the Joule coefficient and Joule-Thomson coefficient is for an ideal gas? One step further. Do we know what the answer? Like, what is the Joule-Thomson experiment coefficient and Joule coefficient for an ideal gas? So that's going to be 0, right? Because for both processes, we're keeping my enthalpy or internal energy as constant, so these delta T must be 0 for that process, for ideal gas only. But in reality, we don't have ideal gases, right? But so that's why these experiments are still very useful. Okay, hope I didn't confuse anyone by saying that, but we'll revisit that later on. Now, thinking about the process of a reversible adiabatic process of an ideal gas or perfect gas. The goal here is to write out an expression of temperature and volume for a reversible adiabatic process. Right. So again, reading what we know about what's given in the setup, we have adiabatic process. So that tells us there's no heat transfer. So my heat is 0, or any infinitesimal change of heat is also 0. Second part, we have a reversible process. So that tells us we can use the dW reversible equals to negative PdV. And we have perfect gas. So that perfect gas tells us we have PV equals nRT, my du equals Cv dt, my Cv is a constant. I need to add that in. All right. And now, can you use the first law of thermodynamics to derive a relationship between temperature and volume for any reversible adiabatic process of an ideal gas? all right, using the first law of thermodynamics to derive a general expression of the relationship between temperature and volume for any reversible adiabatic process of an ideal gas. So what about you do it on your end, I do it on the board, and then later on we'll walk you through in what we are thinking when we're talking about this kind of problem. So first step, since we're using the first law of thermodynamics, what we're writing down, well, is the expression of the first law of thermodynamics, which is du equals to dw plus dq. And then putting in the information from the question. Now we know it is adiabatic process, so my dq equals to 0. We know that it's ideal gas, so my du equals cv dt. And for reversible PV work, my dw reversible equals to negative PdV. So our equation of the first law in this specific setup then becomes cv dt equals to negative PdV, which for ideal gas, we know that PV equals to nRT. We can write it as nRT over V dV. All right. And we're talking about a relationship between volume and temperature. So let's move volume with volume, temperature with temperature. And moving all the constant term to one side of the equation. What we end up getting is, well, Cv over T dt equals to negative nR over V dV. You can also move Cv on the right-hand side. That doesn't really change anything. Or let me actually do that. All right, with this expression, that becomes quite straightforward to take integral on both ends. That's something we can do, to take integral on both ends of the equation to get, well, 1 over T dt equals to negative nR over Cv, these are my constants, and 1 over V dV. All right, then doing that integral then becomes ln T2 over T1, 2 is some random state, 1 is some random initial state, equals to the negative nR Cv. Similarly, we have ln V2 over V1. All right. And moving this negative NR over CV inside the lowing term becomes lowing T2 over T1 equals to lowing V1 over V2, since we have the negative sign, and NR over CV. Again, this V2 over V1 becomes V1 over V2 because of this negative sign. A little bit of the logarithm math. And then whatever in the lowing are the same if the logarithm of that property is the same. So we can take it out as T2 over T1 equals to V1 over V2 NR over CV. All right. So this is the general expression of temperature and volume if we're talking about a perfect gas or ideal gas, adiabatic, and constant CV, reversible PV work only. All right. Any questions on this part? Yes.
Would CV be dq over dt? Couldn't
Which one is it?
CV, that's dq over dt. Wouldn't that just
CV is not necessarily dq over dt. Now, CV is by definition, well, CV is dqv over dt. So if you want to use the CV equals to dq over dt, we must specify that's a heat at constant volume. Or, again, whenever in doubt in that kind of question, thinking about what exactly is the definition of CV. So this is the only very uniformal definition of CV. All right, so CV by definition equals a partial derivative of internal energy over temperature at constant volume. But in special cases, we can write, for example, CV equals to dqv over dt. That is because dqv equals to du for special cases. So that's the only uniformal definition of heat capacities. So whenever you're in doubt about why don't we use this relationship, thinking about what exactly is the definition of the term we're referring to. So this is a more formal definition of heat capacity. And then later on, we have special cases that's linking, say, QV with du, and that's linking CV with dQV. But this is not, generally true. Yes?
When would CV not be?
What's that?
When would CV not be?
What do you mean by CV? Whenever we're not talking about an ideal gas, then my CV is not necessarily a constant. So for ideal gas only, my CV is a constant. More often, it's not a constant. Like the example question we did, remember we talked about the specific heat of a piece of metal. You drop it into the water and measuring the specific heat at that initial temperature. You can do that experiment multiple times to get a curve of CV versus temperature. Right? So CV is typically not a constant. It is only a constant for ideal gases. Okay, any other questions? All right, so let's move on to our next part. So at the end of this chapter 2, we want to do a quick summary. So far we have covered most of the materials in our chapter 2, which is discussing the laws of thermodynamics, the first law of thermodynamics. Now, as a quick summary, let's just go over it together, what we learned when reading the problem. In this case, we discussed several different types of thermodynamic processes. You might see a combination of several of them together in one question. But let's just look at each of these keywords and what does that tell you. First one, cyclic process. Now, remember what we're talking about when we're saying a process being cyclic. We're saying this process have the same initial and final thermodynamic state. So for that say, a cyclic process tells us my initial and final thermodynamic state are the same. So we know our state function, the change in any of the state functions, will be the same. All right, so in this case, we have delta U equals to delta H equals to delta V, which is volume, not potential energy, delta T equals to delta P equals to 0 for cyclic process. All right. The other way to put this question is, let's say we give you a new function, some random function, let's say smiley face. And we say this delta smiley face always equals to 0 for cyclic process. Can you tell me something about the smiley face? Right, so it must be a state function. So that's the first one. Second one, reversible processes. So a reversible process, by definition, is saying the system is always infinitesimally close to equilibrium. So any infinitesimal change on the system will put it back into equilibrium. So for this one, so far we only covered the dW reversible equals to negative PdV for PV work. All right, there are different types of work on top of PV work. For example, electric work, it is not PV work, but we have like new sets of electrochemistry rules for electric work. But for PV work only, your reversible work equals to negative PdV. Yes?
What does PV work exactly mean again?
Well, say I have this piece of paper. Let's say I make it a cylinder or something. We have gas in there, right? And then squeezing it is like a type of PV work. We're talking about the change of volume inside of the system, or change of pressure, or apply pressure on the system. So you can think about PV work more connected to like mechanical work, like we're applying force on that system to change its volume or so on. There are different kind of work, right? We have chemical potential that we care about as chemists. We also have electric work that we care about. So for this thermodynamic class, we're focusing on PV work only. Once we solve PV work, those things will be quite intuitive for you. Okay. And there's one more type of reversible process, one more property of the reversible process we will talk about in chapter 3, which is while we have dW reversible. What does dQ reversible mean, right? The reversible heat transfer. What does dQ reversible tells us? So that equals to temperature times the infinitesimal change of entropy. This we'll talk about it in chapter 3. So a reversible process tells us two different things. Your dW reversible equals to negative PdV, dQ reversible equals to TdS, which we will discuss in chapter 3 or next lecture. All right, then isothermal process. So what isothermal process tells us is, well, this process involves my total change of temperature equals to 0. So for ideal gas, we have internal energy only a function of T, my enthalpy only a function of T equals to 0. But it is, again, for ideal gases only. All right. And keep in mind, we went over the derivation that for isothermal processes, even if my total change of internal energy and enthalpy are 0, the heat transfer is not necessarily 0. But for adiabatic processes, whenever you see an adiabatic process, it doesn't matter what system we're talking about. An adiabatic process only tells us my system is separated from the surrounding by an adiabatic wall, so no heat transfer is allowed. It doesn't matter what my system is. So dq equals to 0 and q equals to 0 for adiabatic processes. Again, like in thermodynamics, we have a lot of terminologies like adiabatic, isothermal, isochoric, isobaric, etc. So get very familiar with these terms and know how to translate these thermodynamic terms into this kind of equation that can help you solve a problem. All right. And then we have two more. Like we say, we have isochoric process, which is constant volume. So if only PV work is considered, then my work equals to 0 if there's no volume change. Or the other way to put it, if we're only talking about PV work, there's no volume change, well, my system is not doing work on the surrounding or vice versa. So work equals to 0 for only PV work system and isochoric processes. And then for isobaric processes, this one we didn't talk too much about, like constant pressure process. Well, one thing you know, for constant pressure, for doing the integral for the WPdV, you can take the pressure out. Or we use the constant pressure to give enthalpy a physical meaning, or say delta H equals to QP. So these are the general summary of what we covered. Like, get familiar with it, because in the following kind of problem, you will need to use these things quite intuitively. So this is one of the example problem in your chapter and summary, saying like, well, for each of the following processes, just write out whether or not each of these quantities, heat, work, delta U, and delta H, are they positive, 0, or negative, right? We don't have to do any calculation, just simply doing a mental gymnastic and try to derive whether or not these processes are positive, 0, or negative. So we want to work on this together, and let's see what's the best way to do it. I think in my blank note, can you check, like, did I rewrite the problem for you? I think I did. So we can just go over these problems like one by one. I only have 10 minutes left, so let's see if we can finish all of them. But if not, we'll just try it yourself. All right. So the first thing, reversible phase change at constant temperature and pressure. So we're talking about a solid benzene melting into liquid benzene. In the process, we know that the density of the solid benzene is larger than the density of liquid benzene. And we also tell you, like, the heat of benzene melting at constant pressure is larger than 0. Or the other way to put it, the heat of fusion or heat of melting is a positive number. That's also quite intuitive. So what do we know? We want work, heat, delta H, and delta U. Right, so in here, there are several things we know. First thing, when we're looking at melting, the change of the volume is a very small number and a super slow change in the volume when we're talking about melting of that solid benzene. Right, so the change of the volume is very small. Thus, we're using W reversible equals to negative V solid, that's initial, over V final, PdV. Right, so pressure is a constant, we can take it out. That's negative pressure times V liquid, V final minus V initial. So V liquid minus V solid. So since the density of your benzene solid is larger than the density of your benzene liquid, my volume here is, the final volume is larger than my initial volume. So this term is positive. So and occasionally I write like plus VE tells it's positive, minus VE is negative. So in this case, whatever in the parentheses is positive, the change of volume is positive. So the overall work is going to be a negative number, but a very small one. All right. And for QP, well, QP in this case just equals to my delta H, because, well, the delta H equals to QP at constant pressure. So delta H equals to QP equals to my Q benzene melting, which is a positive number. And then we can use our first law of thermodynamics, delta U equals to Q plus W. And since in this case, my W is going to be a very small number, my delta U is expected to be a positive number. All right. No calculation, just simply using the definition of the terms and also what we know about these processes to answer the question. Next up, let's skip number B because this is effectively the same thing. The only difference is the density of the water solid is smaller than density of the liquid solid, so one of the things is changing, but the rest of the story keeps the same. Let's look at the reversible adiabatic expansion of a perfect gas. So this we went over together, right? So what we know about this question, we have reversible, so W equals to negative PdV, adiabatic, Q equals to 0, expansion, so V final is larger than V initial, or delta V equal is positive of a perfect gas. Right, so perfect gas, we have PV equals to nRT, H is a function of T, U is a function of T, and my CV and CP are constant. So again, what we're looking for is, well, Q equals to 0. We can just write it out. The heat is 0. So then my work, or, well, you can do it in two different ways. In this case, we can do it in, like, say, delta U equals to the V initial, V final, well, T initial, T final, I'm sorry. And that gives us CV dt. And thinking about the temperature change, for reversible adiabatic expansion, we derived our expression, which is here, the T2 over T1 equals to V1 over V2. Right, so my gas expansion, so my temperature is dropping, so my T final is smaller than T initial. And as a result, my delta U equals to CV times T final minus T initial. So this one is negative. And this delta U must be negative. Right. Same thing for delta H. My temperature is dropping for a perfect gas, so my delta H must be negative. Well, since heat is 0, my delta U and delta H are negative. My delta U equals to Q plus W, so my W must be negative. The other way to think about it, it is a reversible expansion, right? So my work equals to negative PdV. It is expansion. My system is doing work on the surrounding. The work also must be a negative number. So you can do it in two different ways. You can either do like Q equals 0, work is negative, so delta U is negative, and so on. Or you can do it what we did, right? Q equals 0, the temperature is dropping, so delta U is negative, and vice versa. But nevertheless, you'll get the same result. So a typical question we will ask you on exams or your problem set is, say we give you a process and give you like 4 things to write, like Q, W, delta U, delta H. Later on, we might also include delta S, which is entropy change, and tell us are they negative, are they positive, are they 0, like one or the other. Any questions before we move on? Yes. So here, right, we write out this expression for adiabatic reversible expansion or any processes. It doesn't need to be an expansion. Now, my V1, V2 is the opposite of my T2, T1. So if we're doing expansion, so my V final is larger than V initial, my temperature must be reversed. So temperature initial is smaller than temperature final. Or again, you can do it the reverse way of thinking about whether or not my system is doing work on the surrounding or surrounding doing work on the system. Yes?
Would it also be right to just look at the previous conditions that I figured out? Like the Q would be 0, so if we just use the delta U equals Q plus W, and the delta U is going to be negative, so it's going to be negative delta U is going to be equal to W.
Yes and no. So this is what we did, right? What my approach is write out Q equals 0 and derive delta U is negative, so W must be negative. You can do it reversely, right? You can think about like Q equals 0, W is negative because system is doing work on the surrounding, and hence delta U is negative. It doesn't matter how you get to the answer, we always get to the same answer. That's the good thing about thermodynamics. So you can think about the problem in different perspective, you'll always get up the same answer. So you know you get it right. All right, the last piece of information, I'm gonna skip this one, the reversible isothermal expansion. This one we also did at the beginning of the class, at the first question of the class. And then let's look at this one, the adiabatic expansion of perfect gas into vacuum. So again, adiabatic tells us Q equals to 0. Now this one is a little bit misleading because it's, again, an expansion. But it's going to be wrong if you automatically say, hey, expansion must be work equals to negative because system is doing work. But in this case, we're talking about expansion of perfect gas into vacuum. All right, so my system is not doing any work on the surrounding because we're expanding it into vacuum. So this is the setup of our Joule experiment. And W equals to 0 for this process. So W reversible, this equation is no longer applicable because we didn't say because this process is not a reversible process. Like the expansion of your gas into vacuum, you cannot put it back from the vacuum, right? So that's an irreversible process, so we cannot use that equation. And since we have Q equals to 0, W equals to 0, my delta U must equals to 0, because it equals to Q plus W. And because delta U is 0, we can write out like delta T is 0 because we're perfect gas. It's only dependent on temperature. And hence, delta H equals to 0. All right. So referring back, I think I'm running out of time, but referring back to our original study, thinking about why the Joule coefficient equals to 0 for perfect gas. All right, so this is the end of our chapter 2. We're ready to talk about entropy in our next chapter, which will be super fun. And good luck studying. I'll upload the recording as soon as possible.